Okay, we will go through some important points in the class 11 physics, chapter 10 thermal properties of the matter. Okay, it is a measure of hotness of the body. Okay, the temperature measure of the hotness of the body. Temperature is a relative measure. Heat transfer takes place between the system and the surroundings. Okay, what is heat? Heat is the form of energy transferred between the two or more systems or system and with the surroundings. Okay, the unit is in, you can say, in joules or in Kelvin. Okay, measurement of the temperature. So using thermometer which uses mercury, alcohol, etc. are used, whose volume varies linearly with temperature. Okay, these are what is freezing and boiling point and the standard pressure. So these are the some temperature units. One is Celsius, other is the Fahrenheit unit. Celsius from 0 to 100 degrees Celsius. So this is the Fahrenheit. Fahrenheit is 180 divisions. Okay, different between 32 to 212. So between lower and upper there is 180, but here Celsius 100, 0 to 100. This is the conversion formula from Fahrenheit to Celsius. Okay, this is the lower limit and divided by 180. So here Tc by 100. Boyle's law, when temperature is held constant, the pressure PV equal to constant. Okay, at constant temperature, all the gases obey this law. PV equal to pressure and volume is constant. That is Boyle's law. Another law is Charles' law, that pressure is held constant and volume divided by temperature equal to constant. That is Charles' law. So here the pressure versus temperature of the this low density case kept at a constant volume. Okay, so here it meets at here, that is the absolute zero. This is for the different cases. So important thing is that all the gases meet at one point, that is absolute zero. Okay, this point you see all the points, temperature versus pressure graph, at one point they all meet at only one point. This is called absolute zero. Ideal gas equation, mu is the number of moles. Okay, R is the gas constant, universal gas constant. Absolute zero, that is the absolute zero. Here this is the absolute zero, that is minus 273.15 degrees Celsius. Okay, these are the different scales. See, you see these Kelvin and Celsius scales, they have the same unit size. Here you see between one temperature other the unit is same, scaling is same, but for the Fahrenheit it has smaller scales. Okay, smaller interval, you see, we compare between this and this, it has smaller interval. C and K have the same interval, but Fahrenheit have smaller interval. These are the fixed points on this scale. You see from Celsius and Fahrenheit, these fixed points. 32 is one fixed point, 212. 0 is one fixed 100 degree. But for the absolute that is Kelvin, is 0 is the one fixed point. You see the fixed point dotted line here. Thermal expansion, when you heat a substance it will expand. Okay, on heating it will expand and contract on cooling. Okay, this is called thermal expansion. This is linear expansion, length, expanding in length, linear expansion. Expanding in area, this is the area expansion. Expanding in volume, this is volume expansion. You see this linear expansion related to the area expansion 2 alpha 1. This is volume through 3 alpha 1. So linear expansion, area expansion, and volume expansion. Delta L is nothing but difference in length, that is L final minus L initial. Similarly, area also, area final minus volume also. Coefficient of the linear expansion. These are various linear expansion available for different materials. Volume expansion for different things. See, water has this property, it has at 4 degrees Celsius. This is the highest density, that is the maximum density, lowest volume. You see, this is temperature versus volume graph. This is lowest volume at 4 degree. Okay, here 4 degrees Celsius. That means lowest mass by volume is the density. Lowest volume means highest density. You see, here density is maximum at 4 degree. So, if water did not have this property, lakes and ponds would freeze from due to this property 4 degree, lowest volume, highest density. Linear expansion is inversely proportional to the one temperature. See, this volume expansion coefficient is 3 times the linear expansion. Okay, volume expansion is 3 times the linear expansion. See, when you fix the material, that is when what happens when preventing a thermal expansion of a rod by fixing on ends rigidly, that means there will be a thermal stress will be developed on the material because you are not allowing it to expand freely. By fixing its end rigidly, that means there will be a thermal stress will be developed. This is the area expansion 2 times the linear expansion. So how this formula is arrived from page 4. See, if you substitute for delta L, see, if you substitute delta L equal to L final minus L initial, this is L initial, then you go L initial here, you bring this also here, then you will get that equation. Okay, this equation L final equal to this you will get. Specific heat capacity. So here what they mentioned is the heat required is not constant between the temperature. Suppose from 40 to 20 degree Celsius, suppose 20 to 40 degree you require some heat that may not be same for 40 to 60 also. That is what the double the quantity of heat required rising twice the temperature of the same amount of water. Okay, the heat required is different at different temperature. The amount of specific heat, this is heat capacity. To change the temperature from T to delta T, T plus delta T. So we have a specific heat capacity that depends on the mass. Okay, specific heat, the here m, temperature of unit mass, okay, by the unit. So here molar specific heat rate as the number of moles is given instead of mass. For the water as having highest specific heat capacity. For this reason, water is also used as a coolant in automobile radiators. Calorimetry, that is used to measure the heat, for the measurement of heat. So heat lost by the one body is heat gained by the other body. Okay, heat lost by the hot body is equal to heat gained by the cooler body. To measure the heat is a calorimeter. Heat given by the aluminum sphere is equal to the heat absorbed by the water and the calorimeter. Okay, heat lost by the aluminum is equal to heat absorbed by the water and calorimeter in the calorimeter problem. In the steady state, heat lost by the aluminum sphere is equal to heat gained by the water plus heat gained by the calorimeter. That is important. Change of state. See here, you see at this temperature won't change, okay, till all solid is converted into liquid. Same temperature will be maintained here, okay, at the melting point till all solid is converted again, then it will start to rise. Here also temperature is maintained here. Okay, what is normal melting point? That is measured at the standard atmospheric pressure. What is triple point? Okay, triple point is where this sublimation solid to vapor and liquid to solid and this vapor curve, sublimation curve, vaporization curve, fusion curve, all meeting at the one point, that is called triple point. Okay, the temperature and pressure at which the fusion curve is this curve, okay, vaporization curve this curve, and sublimation curve this curve, all meet, and all the three phases of this substance coexist is called the triple point. Okay, this is all phases of the substance exist at this point, triple point, for the triple point. Okay, this is for the carbon dioxide and this is for the water. Normal boiling point, the boiling point of the substance at the standard atmospheric pressure. Okay, normal boiling point. Sublimation solid to liquid, solid to vapor, solid state to vapor, sublimation. Latent heat, the amount of heat per unit mass transferred during the change of state of the substance is latent heat, the amount of heat per unit mass. Okay, okay, amount of heat per unit mass, m, q by m is the latent heat. This is the quantity of heat per unit mass. These are the various heat values at different phases. Okay, gas phase and liquid phase. Okay, and phase transitions. heat transfer. Okay, there are three modes: conduction, convection, and radiation. Ways of heat transfer. This is conduction by physical interaction is there. Convection. Okay, here radiation. There is no, without any medium radiation. Conduction, heat takes place in conduction from the hot end of the rod through the different parts. Okay, physical interaction, conduction, like this. This is the length of the rod. Okay, this L, heat transfer. TC is the hot end, TD, that is TC is at higher temperature than the TD. This L is the length of this rod. Thermal conductivity, you see copper, thermal conductivity copper is more. Silver is more, that may be more costlier than copper. Under steady state condition, heat current H1 through the iron bar is equal to the, this is for this problem actually. Convection is the mode of heat transfer in actual motion of the matter, in possible only in the fluids. Okay. See here, during the daytime the air flows from land to the sea, but in the night time from sea to the land. Okay, the important. Daytime land to the sea, the night time sea to the land. So the equator and polar region receives unequal amount of heat, solar heat, okay, sunlight. Equator has an eastward speed of the 1600 km per hour, while zero close to the poles. Radiation, no medium is required, okay, for the transport medium. The amount of heat that a body can absorb radiation depends on the color of the body. Okay. Black body radiation. This is at the different temperature. The energy emitted versus wavelength for a black body at different temperatures. This is sunlight. Okay. So based on this wavelength we can compute the temperature of the planet also. Energy emitted per unit time. This rho is the Stefan Boltzmann constant, this rho. Okay, this is the heat loss between the hot body and the surrounding. Ts is the surrounding temperature, T is the temperature of the body. Newton's law of cooling. Okay, this is dq by dtk into d. This is the T1 is the surrounding temperature, T2 is the body temperature. K is a positive constant. According to Newton law of cooling, the rate of loss of heat minus dq by dt of the body is directly proportional to difference in temperature. Okay. Okay, summary, you can go through this summary. This is the conversion formula, ideal gas equation, Kelvin absolute temperature, this relation, volume, the length expansion, linear expansion, volume expansion. Okay, these are the dimensions of the various quantities. Okay, we will go through the exercise. Okay, the triple points of the neon and carbon dioxide are this. Okay, 24.57216 Kelvin respectively. Express these temperatures on the Celsius and Fahrenheit scale. Okay, these are given in the absolute scale. We have to convert into Celsius and Fahrenheit using formula page 2 and 3. Okay, this is the Fahrenheit to Celsius, and here we have the Kelvin Celsius. Okay, so this is the conversion. Kelvin equal to Celsius plus 273.5. Okay, from that we can compute the Celsius. So this is the Fahrenheit to Celsius conversion. This conversion, this, okay, using these two formulas. So you can, for the neon, this is the much is the Kelvin. Okay, Kelvin, Celsius and Fahrenheit. For the carbon dioxide and this one. Two absolute scales A and B have a triple points. Okay, 200 and 350B. Okay, triple point is 273.16 is the triple point. Okay, 200A and 350, they are two different scales. Okay, what is the relation between the triple point A and triple point B? So 200A equal to 273, that is 0.16 Kelvin, that is the one scale, that is scale A. 350B equal to 273.16 Kelvin, that is in the scale B. Okay, so that means B is a smaller scale than A. Okay, from that, okay, because both are equal, so this should be smaller scale. Okay, 200A equal to 350B, then after that you will get this ratio, that is TBB by TA. TB means triple point of B. Okay, triple point of A into scale A equal to triple point B. So T A by TB equal to B by A. Okay, B by A. So now here TB by TA equal to A by B equal 350. So that is 7:4. So which relation you use? So TA by TB means it will be 4:7. So you have to remember that. The electrical resistance in ohms of a certain thermometer varies with the temperature according to this relation. The resistance is 101 at the triple point of water and okay at the triple point at the normal melting point. What is the temperature when the resistance is this? So if you find this value of the alpha is not given, so if using this given values 106 and 165, find alpha, then we can find the temperature. So using this, we are first finding the alpha. Okay. So this side you are bringing, then you find given the value 165 or substituting, you find the alpha. Then using the alpha you find the temperature. Okay. This temperature. Okay, this is the triple point and this is the temperature. At that temperature the resistance will be 124, 123.4. Okay, 123.4. Okay, this is the temperature, 384.33 Kelvin. Answer the following. The triple point of water is a standard fixed point in the modern thermometry. Why? What is wrong with taking melting point of the ice and boiling point of the water? This triple point is a constant, that is 273.16, but the melting point, boiling point varies with the pressure. That is why we use the triple point, a fixed point. Okay. There were two fixed points in the original Celsius scale as mentioned above, which are assigned 0 degree, 100 degree. On the absolute scale, one of the fixed point is the triple point of water, that is 273.16. What is the other fixed point? That is absolute 0, page 3. So they are saying for the Celsius there are two fixed point 0 100. For this absolute scale they are given one fixed point is triple point somewhere here. They are asking what is the other fixed point. This is absolute 0 here. See this fixed point here. The absolute temperature is related to the this Celsius. On the Celsius scale, T is equal to, okay, 0 degree melting. Okay, this much. Why do we have 273.16 in this relation? Not, see, this is the triple point, not the melting point of the ice. So here in this relation we use the melting point of the ice, not the triple point. See here, see, we are using absolute 0, that is not the triple point. Okay, this is the absolute 0 value, not the triple point. It's taken as the 0. What is the temperature of the triple point of water on the absolute scale, whose unit interval is equal to that of the Fahrenheit scale? See, the Kelvin and Celsius scale are same, okay, as I already shown you. See here, these two scales are same, they are the equal height, but this only is different. So from Kelvin to Fahrenheit conversion or Celsius to Fahrenheit, both using the same formula. Okay, triple point, okay, T Fahrenheit equal to 9 by 5 into T Kelvin. Okay, after that you will get this 491, okay, units, 1 units. two ideal gas thermometer A and B, oxygen and hydrogen respectively, the following characteristics are made. Okay, triple point of water in this thermometer, this is a value, and this thermometer this. Normal melting point of sulfur, this thermometer reading, this thermometer reading. Okay, what is the absolute temperature of normal melting point of sulfur as read by the thermometer A and B? As per the Charles law, volume by temperature equal to constant pressure at the constant pressure, atmospheric pressure. Okay, this is PA, that is pressure at the thermometer 1 divided by the temperature equal to pressure at thermometer divided by the time. Okay. For the thermometer B, again we use because this is equal to constant. Okay, then you will get this temperature value. So there is a difference. Okay, so this is not ideal gas. Okay, 392.7, 391.98. Okay, they are not same because they are not the ideal gas. So this experiment should be done in the low pressure condition, then only you will get the accurate value. Okay, this is the triple point of water. So now they are asking a normal melting point of the sulfur as read from the thermometer. Okay, triple point we know 273.16. Normal melting point of the sulfur, that is we have to find out. So this is the melting point of the sulfur. Here it is 392.7 Kelvin and 391. Okay, this is not ideal gas. Why do you think the reason behind the slight difference in the answers of the thermometer A and B? Okay, that is they are not ideal gas and the experiment should be done at the low pressure condition to get the accurate value. Okay. A steel tape 1 meter long is correctly calibrated at the 27 degrees Celsius. The calibration is done at the 27 degrees Celsius. The length of the steel rod measured by this tape is found to be 63 centimeter on a hot day when the temperature. Okay, the calibration is done at 27 degree, but the measurement is done at the 45 degrees Celsius. So there will be a change in the length of this tape. It will not be 1 meter because temperature rise, it will length will expand. What is the actual length of the steel rod on the day? Coefficient of the linear expansion. Okay, this is similar problem, page 6. This problem is similar to that. Okay, so here I already told you how we got the formula from the delta by L equal to alpha into delta t. Delta t is nothing but T2 minus T1. Okay, so this problem is similar to that one. Okay, so here you see delta L by L equal delta L has meant length final minus length initial. Okay, So this is the change in length in the initial length divided by the original length. Then you take this L this side. So this L and this L is same. So after you substituting, you will get the what is the tape length at the 45 degrees Celsius. Okay, it was calibrated at 27 and at 45 it will be slightly more, so that is 0.02 centimeter more. Earlier it was 1 meter and 100 centimeter, that is. So now it is now using that value, now you find the rod length. Okay, yeah, it was measured 63 and calibrated with the 27 degree. Now you measure the, so this will be the new actual length of that rod, calibrated at the lower temperature and used at the higher temperature. That is why this difference is there. A large steel wheel to be fitted onto the shaft of the same material at 27 degrees centigrade Celsius. The outer diameter of the shaft, okay, the diameter of the central hole, okay, this wheel is slightly lesser than the shaft, but the shaft is cooled, so this will come down. This contraction will take place because it's cooled in dry ice. At what temperature of the shaft does the wheel this shaft, this length is equal to this length, then it will be slip onto the shaft, assuming okay. Okay, again you are using the same formula. Now we are using the final length should be this, and this is the original length. So we have to find out the temperature, at what temperature then these two will equal. Okay, so this is the at a negative 69 degrees Celsius. So then only 807 will become 8.69. okay, at the temperature wheel will slip onto the shaft. A hole is drilled in a copper sheet. The diameter of the hole is 4.24 centimeter at the 27 degree. What is the change in the diameter of the hole when the sheet is heated? Okay, when you raise the temperature, the hole will expand. Okay, coefficient of the linear expansion, page 4. Again, page 4, I already shown you that linear expansion, area expansion, volume expansion. Okay, this is the linear, area and volume expansion. So here we are using area formula, but similar, only here 2 alpha. Okay, 2 into linear expansion. So you will get this formula if you use delta A, area equal to pi r square, r equal to d by 2. So pi d square by 4. Pi d square by 4 minus pi d square, again this area difference. So here pi and 4 will cancel out. That finally you will get this formula. Okay, you do it and you will set the area expansion. So now this much. So now the new diameter we are finding. Okay, this is diameter square, then diameter, the new diameter is root of this is 4.25 centimeter. So now 4.25 minus 4. This is the expansion, 0.01 centimeter. A brass wire 1.8 meter long and 20 is held taut with tension between the two rigid support. If wire is cooled to a temperature, then there will be a contraction. What is the tension developed in the wire? If the diameter is this, okay, See here, based on this Young's modulus also is given. So they are asking the tension, that is nothing but the force. So based on what is given and what they are asking, see, you should use that formula. Okay. So now already you know the Young's force by area divided by the strain, that is delta by L. So we will be use that formula. Young's modulus stress by strain, force by area is the stress, delta by L is the strain. Okay, from thus you can find the delta L, force into from this solid chapter. This Young's modulus is from the some other chapter, so you will get the formula from that chapter, other chapter. So A into delta L. Then from this delta L equal to force into length divided Young's modulus into area. Okay, that is one formula. Force is nothing but tension or the force. Now there is other formula here in this delta L by L equal to alpha delta T, that is a linear expansion coefficient. Okay, so from here you find the delta L alpha. Okay, now we have to equate this with this equation. Okay, this and this equation, then from that you find the force. Okay, that is negative 377.17 newtons. So negative means because it is inward force, that is contraction. Okay, that is why negative value is coming. Because we are cooling down, it is cooled to temperature of this. So what is the tension? That is the contraction. A brass rod of the 50 centimeter length, 50 centimeter and diameter 3 mm is joined to a steel rod of the same length and the diameter. What is the change in length of the combined original length or at 40 degrees C? Is there a thermal stress developed? Here you see from the problem itself we can find out there is no thermal stress, because they are not tying the ends. This is freely expanding. See here, a brass rod of length is joined to a steel rod of the same length. They are not tying it in any end. So the expansion is free, though there will not be any thermal stress. Okay. Okay, here delta by L equal to, so this is the expansion for the brass, and similarly for this steel, and this is the expansion. Now the total expansion is this much. No thermal stress because it is not tied in any end. Okay. 11. The coefficient of the volume expansion of the glycerin is given. What is the fractional change in the density for the 30 degree? Delta T is given, rise in temperature. Okay. Here again page 4, that formula you can go through. Delta V by V equal to alpha V, coefficient of the volume expansion. They are given. Okay, if you again use this formula, then you will get finally this. So from this, the density equal to mass by volume. Okay. So the volume finally volume initial plus, okay. Now you substitute for this density, that is mass by volume. You take out mass common, then mass will cancel out. M will cancel out both top and bottom, numerator and denominator. Then you will get this. So you will finally initial by final minus 1. So after you substitute this, then you will get this G minus 0.0145. Okay. because density decreases. Negative. Rise in temperature in the block 2 point. Okay, not this. Change in density for 30-degree rise in temperature. Okay, rise in temperature. Okay, 30-degree rise in temperature decreases the density. A 10 kilowatt drilling machine is used to drill bore in a small aluminum block of mass. Okay, this much. How much is the rise in temperature of the block in 2.5 minutes? Assuming that 50% of the power only is used the heating machine. Okay. So again, from the given info, you should know how to use which formula should be used. Okay. So this formula. Okay. Delta Q equal to M mass into specific heat capacity, the delta T power into time. Okay, that is the total energy. In seconds you are converting 2.5 minutes into the seconds. Okay, this much the power, but only 50% of the power is used. So this is the final used power. So now this is the total power used. You have to find only the temperature difference. So from this formula, delta T equal delta Q by ms. Then you will get this. The copper block of mass 2.5 kg is heated in a furnace temperature 500 degrees, then placed in a ice box. What is the maximum amount of ice that can melt? Specific heat of copper, heat of, okay. See, so this page 12, latent heat. So here this is the relation mass, latent heat and the amount of energy. Again we are using M as delta T. Okay. So you will come this value, then L equal to Q by M. M equal to, so after that you will get this. This is the gram of ice. This is L is latent heat. In an experimental specific heat of a metal, 0.2 kg block of the metal at 150 degrees is dropped in the copper calorimeter. So here is important is the water equivalent of 0.025 kg. That is important here, water equivalent. So we are going to use the specific heat capacity of water here, because the mass is given in the water equivalent containing this much. Final temperature, okay, specific heat capacity. Okay, this example is similar. This problem in this example, heat in the steady state, heat lost by the aluminum spherical, heat gained by the water plus heat gained by the calorimeter. Okay, so this problem is similar to that problem. Okay. Heat lost by the metal equal heat gained by the water plus heat gained by the calorimeter. Okay, this is the heat loss equal to heat gain by water and the calorimeter. So we are going to use the same this S specific heat of the water, because this mass is equivalent to the water equivalent they are given. Okay, this is for the water and this is for the calorimeter. Okay, this M and this M, then into S delta T, those two are common. Okay, so these are different, these two are common. So now the SM of the metal, so it comes out to be 0.433 joules this per Kelvin. Given below are the observation of molar specific heats of the room temperature of the sum of the common gases. Okay, so the measured molar heat of these gases are markedly different from the monatomic gases. Typically, molar specific of the monatomic gas is this range. Explain the difference. These gases are the diatomic gases. They have the other motions in addition to the translation motion. So the more heat is required. Okay, specific heat capacity, molar specific heat capacity of this diatomic gases is more. What is this molar specific heat capacity? Okay, (16). A child running at the temperature is given a antipirin, a medicine that lowers the fever, which causes increase in the rate of evaporation of the sweat from his body. Not down in 20 minutes. What is the average rate? Okay, okay, these things is given 16. Heat lost by the child, delta equal to ms into delta T. This is the mass of the child. Specific heat of the water. See, here we are using the different unit. Okay, so this is 1000 calories per kilogram something. Okay, 1000 calories per kilogram per degree Celsius. Okay, the 4186 here, this is different from this. Here we are using the different unit for our convenience. So after that, this is the 50,000 calories loss. So Q equal to M equal to Q by L. 50,000 divided by the L, that is the latent heat. So after that, this is much kg, this much gram, sorry. So the average rate of the evaporation equal to for this many minutes. Okay, this many grams, so 4.3 gram per minute. A thermometer ice box is a cheap and efficient method for storing small quantities of the cooked food in summer. A cubicle worth of this much dimension, okay, 4 kg of ice put in the box. Estimate the amount of ice remaining after 6 hours. Okay, the outside temperature is this. rate of heat flow. Okay, this is the formula. Tc is greater than Td. Okay, so A is the surface area, that is cube 6a square. A, that is in meter, is 0.3. Okay, now using this formula, Ka, then this difference in temperature, this is also in meter. Okay, this is the thermal conductivity, K 0.01. so this much is the heat Q equal to ml. Okay, so remaining will be the ice left. So this much is melted, so left ice will be 4 kg minus this much. Okay, this much ice is left after 6 hours. So here this time we are using for the 6 hours in seconds, minutes and seconds. The brass boiler has a base area. It boils the water at the rate of 6 kg per minute. When placed on the 6 kg per minute is boils. Estimate the temperature at part of the flame in contact with the boiler. Okay, that flame temperature will be different from that water boiling thing. It will be more than that. Thermal conductivity of this, okay, 18. Heat supplied to the water equal to heat required. This much heat, this is flame, this is the water temperature. Flame temperature is higher than the water temperature. This time, then length equal to this much. This is from Q equal to ml formula. This is for the water and the flame. Then from this you find out this difference in temperature. This is in seconds, we are converting into the seconds. This is meter, K, then A. So temperature of the flame, this is the difference in temperature. So the flame temperature will be water temperature, boiling temperature plus this difference in temperature. Flame temperature equal this right side will become plus 137 plus TW will come. So this is the flame temperature. Explain why body with large reflectivity is a poor emitter. Because it is a poor absorber, so it is a poor emitter. So because it is a reflecting everything, most of it. A brass tumbler feels much cooler than the wooden tray on a chilly day. Because brass is a good conductor that conduct heat from our body to the tumbler, but wooden is a poor conductor. So wood is not conducting, it's a poor conductor. An optical pyrometer for measuring the high temperature calibrated for the ideal black body rays is too low value for the temperature of the red hot iron piece in the open. Okay, in the open place red hot iron need that reading is low, but gives the correct value of the temperature when they place in the furnace. Okay. See, this is the radiation formula. This is the surrounding temperature. So this is the body temperature. In the open place, the surrounding temperature will be less. So here radiation will be more in the open. Okay, that is why you will get the low value. But within the furnace, the surrounding temperature will be more. Okay, so the radiation will be less, heat loss will be less, so that we will get the accurate thing. Okay, here surrounding temperature that matters, the radiation will be less inside the furnace, radiation loss, but in the open it will be more. The earth without its atmosphere would be inhospitably cold, because without the atmospheric gases all heat will be reflected back, radiated back. So so due to these atmospheric gases it is absorbing some heat. Heating system based on the circulation of steam are more efficient in warming the building than the based on the circulation of the hot water. So steam has high latent heat value than the hot water. Body cools from this much, if 80 to 50 in 5 minutes. Calculate the time it takes to cool from 60 to 30. The temperature of the surrounding is 20 degree. This is Newton's law of cooling. Okay, this one. So here this T1 is the outside temperature. This is the body temperature T2. So here for the body temperature T2 we are taking the average of the initial and final temperature. This is the outside temperature. Okay, now first you are finding the K, thermal conductivity. Then using K, we are using it to find out the this temperature. Sorry, times. Okay, from 60 to 30 degree, this much 9 minutes it will take. Okay.